Okay, we are doing refraction. We learned about refraction and then different cases, including critical angle and total internal reflection. Okay, in this lecture, we are going to see how image forms because of refraction. Okay, image formation. Image formation. Okay, let's say that I have two mediums. This is mu1, one medium, and here I have, let's say this is mu1, this is mu1, this is mu2. Object is kept here. This is my object. This is my object. Okay. Someone is looking from outside. My observer is here. Not outside, but in the second medium. Observer is in second medium. So I have this medium 1. Okay. Medium 1, mu1, in which object O is kept. Okay. Someone is looking from the other medium. Okay. Now, where this object will appear, let's say that, let's take one light ray. We know that to form an image, I need minimum two light rays. I need minimum two. One light ray I am taking which falls normally on this interface. It goes without deviation. Okay. Let's say that this point is P. This is my object here. I need one other light ray. Okay. Let's take this light ray. Okay. Now this light ray, depending on the medium, this is my incident light. Now, depending on the relative values of refractive indices, it can either bend towards normal or it can bend away from normal. Okay. So let's imagine that mu2 is less than mu1. Let's say, okay. In that case, it will bend away from normal, like this. Okay. Now, if my observer is present in this medium, so this observer is receiving these two refracted light rays, okay, and then this observer will see that these two light rays are actually coming from a point here. Now, what kind of image this will be? This will be a virtual image. A virtual image. Okay, a virtual image. Now, let's try to find out where this image will be. Let's say that this angle here is theta 1, okay, and the angle here, this angle of in the second medium, okay, this angle is theta 2. Okay, let's apply Snell's law at this point. Let's say that this point is Q. Okay, Snell's law, what it says, mu1 sine theta 1 is equal to mu2 sine theta. And what it tells me? What it tells me is that the location of image will actually depend on from where you are looking at it. A very important point that we generally miss this point. Okay. The location of this image is not fixed. It will depend on theta 1, it will depend on theta 2. Okay. If my observer is here, for the same observer, the image will appear somewhere else. If the observer is right here, that means this point is very close to this point. This point is very close to this point. Okay, that case is known as near normal incidence. Okay, for near normal incidence. What it means? That means I have this object here. I am looking from a point which is just above this. Okay, that is known as, so I am directly looking down towards the object, directly looking down. Okay, in that case, this point here will actually be very near here. That is known as near normal incidence. Near normal. The incident light is near the normal. Okay, for near normal incidence, theta 1 and theta 1 is theta 1, theta 2 are very small. Okay, so we are using this small angle approximation. Small angle approximation. Okay, sin theta approximately tan theta approximately theta. If theta is very small, then for such cases, for near normal incidence, I can write mu 1 tan theta 1 is equal to mu 2 tan theta 2. Okay. Okay, do you see this? Do you see this? Now mu 1 tan theta 1, this is theta 1, this also is theta 1. It will be PQ over PO. PQ over PO. This becomes tan theta 1. This will be equal to mu 2. This whole thing is theta 2. That means this whole angle here, this angle from this is theta 2. Okay, so this angle here, this whole thing is theta 2. Then this also becomes theta 2. Okay, do you see? In that case, tan theta 2 will be equal to PQ over PI. Okay, what do I get? What do I get is PO over mu 1 is equal to PI over mu 2. Is that fine? Is that fine? Now using sign convention. Use the sign convention. This distance is known as object distance. This is object distance and this is image distance. Okay. Sign convention. At this point reflection is happening. Okay. So I am going to measure all the distances from P. It's like pole of a mirror of any surface. This is pole here. Light is going upward. So upward direction is positive, downward is negative. Okay. So if I use the sign convention, in that case U will be minus of PO and V will be minus of PI. Okay. So what I have is minus U over mu 1 is minus V over mu 2. Okay. So this becomes one general relation for me. Okay. So V is equal to mu 2 over mu 1 times U. Okay, do you understand this? Okay, now if mu 2 is more than mu 1, okay, then V will be more than U. If mu 2 is less than mu 1, okay, then V will be less than U. Okay, note down this relation. Try to give it a thought. You have done this thing already, I know. This is part of the syllabus in our junior classes or year classes. I know you must have done this thing, but in a different way. In a different way. Here we are doing it in a proper way. Okay. Now, a special case. This is general case. This is general case. This is a flat surface. This is a flat interface. It's a flat surface, image formation. We will write it here. Okay. From flat surface, okay? From flat surface. That's how image forms. Okay, now let's look at one very special case, and that is the case that you have done. Okay, the special case. The special case is like this. Mu 1 is equal to mu, and mu 2 is equal to 1, let's say. This is 1 and this is mu. Okay, in that case what will be V? This becomes 1, this becomes mu, it becomes U over mu. Okay, sometimes we write it this way. This is my, let's say that this is air. Okay, mu is equal to 1 and this is some medium mu. In this medium an object is kept here. This is my object at a distance of d. This is my object. Object is here. This object is at a distance of d. Okay, d. Now when I look at from the outside, from the air, this is one light ray, it goes without deviation. If I take any other light ray, okay, so it goes like this. It goes like this, and when I extend it backward, right, this becomes my image. That's where the object will appear. Okay, so when I look from outside, I'm not going to see my object here. Okay, to me, the object will be here. This becomes its apparent position. Apparent position. Okay, and this distance, the distances. Okay, this is d and this is d dash. Okay, I'm going to clean all this. I'm going to clean this. Okay. Okay, I'm going to clean all this. Now, so V and U. So V is D dash. D dash is equal to D over mu. This U is equal to D. Okay. You also write it as apparent distance, apparent depth. Okay, let me write it here. Okay, let me write it this way. Okay, let me do it again. I will write it here. Okay, we are looking at the special cases. That's the case that we are going to use a lot, and that's the case you have to remember. We already derived the general case. Okay, this is my object here. This is my object. Okay, light ray goes out. And when I extend it, it appears here. This is OI. This is I. Okay. This is the actual distance, D. And this is the apparent distance. Okay, we just derived it. D dash, apparent distance, D dash is equal to actual distance over D over mu. Okay, so D dash is equal to D over mu. The object is actually located here, but when I see it from the outside, and there is one particular way of seeing, I am seeing it normally, only in that case. This is applicable only for near normal incidents. You have to keep it in mind. This relation we are deriving for near normal incidents. The object is here at a distance of d below this interface. Sometimes it is also written as apparent depth. Apparent depth is actual depth over mu. But here I am writing it as distance for one particular reason. We are going to see. Okay. Now, so this apparent depth is going to be equal to d over mu. Okay, all right. This is 1, and this is mu in that case. Now, the object is here. It appears here. This is the shift in the position of object. What is shift? Shift delta is equal to d minus d dash is equal to, so this delta is equal to d 1 minus 1 over mu. What is this? This is shift in the position of object. Okay, this shift you have to remember. Now this is towards the interface, in direction of incident ray. In the direction of incident rays. This is the shift. Okay, do you see this? Okay, now second special case. Second special case is like this. Okay. If this is air, my object is in air. My object is in air. This is my object. This is my object. Okay. Object O. This actual distance here is equal to D. The actual distance from where? from this interface, from where the refraction happens. Refraction happens at the interface here. Now, if I take one light ray here, this is a denser medium. This light ray is going to bend towards the normal. It is going to bend like this. It is going to bend like this. Okay? And when I have one observer here, okay, this observer is going to see the position of this object not here, but somewhere here. To this observer, the object will appear to be located here. This becomes the apparent position. This is D, okay, this distance is D dash. Okay, what will be apparent position here? You can apply the same relation. What was the relation? It was U over mu1 is equal to V over mu2. Okay, what is U? This is U. Okay, this is our positive direction. This is negative. The incident light is downward, so downward is positive. Okay, U. From this point, I have to write all the distances. This is U. It is equal to minus D over mu1. What is mu1? It is 1. Okay, is equal to minus of D dash over mu2. What is mu2? This is mu2. Okay, so what is D dash? It is equal to mu times D. Here also, okay, I find apparent distance. Apparent distance D dash is equal to actual distance mu times actual distance. Distance D. Okay, so D dash is mu times D. Okay, and this is what you have to remember. This is what you have to remember, that the apparent distance is going to be either D over mu, or it is going to be mu times D. Okay, it is going to be either D over mu, so I have to either divide it by mu or I have to multiply by mu to find apparent distance. Okay, now do I have to divide it or multiply it? I can find out very easily if I draw this simple ray diagram. If I draw this simple ray diagram, here I see that the apparent position is more than actual position. That means I have to multiply by mu. Okay, do you see this? Now, if here from the ray diagram I see that the apparent position, apparent distance is smaller than this actual distance, that means I have to divide. So even if you just remember these two formulas, that apparent distance D dash, it is going to be either D over mu or mu times D. Okay, then you are going to solve many problems. Okay, in case we have some complex problem, we have this relation. We will apply that. Okay, now in this case, what is happening is, this is my rarer medium. I am looking from a rarer medium. The object is here in denser medium. The apparent distance is smaller than actual distance. Okay, it's a case like this. Okay, this is water. Water is filled, and there is one object here, and I'm looking from outside. I'm looking from outside. The object appears to be raised. Okay, the apparent distance is smaller than the actual distance. Now here, just the reverse of it. Okay, so some object is outside in air. Okay, and here I'm looking from inside. I'm looking from inside. Okay, so this object will appear to be higher than its actual height. Its actual height is D. Okay, when I look it from inside here, it will appear to be at this height, mu times D. It will increase. Okay, so let's just do this, just this, not much. Okay, in this case, this is very useful here. It's very useful. Okay, 1 minus 1 by mu. Okay, so if you remember this form, what is this? This is shift. Shift in the position of object. Object is kept here, it appears to be here. So this is the shift. D times 1 minus 1 by mu. Or even if you don't remember this, if you remember these two forms, then also you are going to solve many problems. Okay, but it helps if you remember this form also. Okay, let's do few problems based on this. Okay, we are going to keep it simple. Of course, it can be made complicated. Okay, we are going to first do some problems based on this simple special case where one medium is air. Okay, so 1 mu is equal to 1. So that simplifies the problems. Okay. Okay, let's start doing problem. Okay, an object lies 1 meter above water surface. Okay, what is its apparent height from surface when seen from inside the water. Okay, very simple problem. Let's start with this very simple problem. Okay, now second problem. Okay, I have this air bubble. Okay, now the depth of air bubble as seen from two opposite sides appear to be 4 centimeter and 6 centimeter. Okay, what is thickness of slab if mu is 1.5? This is mu is 1.5. Okay, so I have this glass slab. Mu is 1.5. If I see this bubble, there is an air bubble inside this slab. If I see it from one side, it appears to be at a depth of 4 centimeter. And when I see the bubble from the other side, from the opposite side, it appears to be at 6 centimeter. Okay, what is the thickness of this slab? This slab. Okay. Next one. This is 10 centimeters. Okay. Or 10 centimeter thick paperweight. A 10 centimeter thick paperweight. Okay, it's very huge paperweight. Okay, 10 centimeter thick paperweight is kept over a page. Over a page. Okay, that's it. Letters on page appear to be raised by 4 centimeter. Okay, what is the refractive index of material of paperweight? What is refractive index? Okay, let's solve these few simple problems. Okay, then of course we are going to solve many more problems. We are going to do. Just remember this thing, okay, that d dash is going to be either d over mu or mu times d. Most of the cases, this is what is going to solve our problem. Okay, that's it. This is what is going to solve our problem. Okay, when one of the medium is air. This is when one of the mediums is air. Okay, let's try to answer this. First question, I have an object. Let's see, very simple, how to solve all of them very simply. Okay, this is my object here. This is my object. It is kept at certain height and someone is looking at it from inside. Someone is looking at the object from inside body. Okay, with this actual height is 1 meter. Now, how the image will form? This is one light ray. It goes undeviated. If you take any other light ray, this light ray is going from rarer to denser medium. Okay, rarer to denser. It is going to bend towards normal. Okay, it is going to bend towards normal here. So this observer is receiving these two light rays. Okay, when to the observer, both of them will appear to be coming from this point here. This becomes my image. Clearly, the apparent distance from this surface, to this observer, the object will appear to be here. Okay, that means d dash is going to be mu times d. It is going to be mu times d. Okay, that's it. So 4 over 3 into 1. This is 4 over 3 meter. Okay, 4 over 3 meter. Now the next one. Let's answer the second one. Okay, so I have this glass slab. Inside the glass slab, there is one object. That object is an air bubble. Let's say that the actual distance is d1 and this actual distance is d2. So from one surface, the actual depth or actual distance is d1 and from the other side, it is d2. Okay, so what will be thickness? This thickness d will be d1 plus d2. Okay, makes sense. Now, when I look it from one side here, okay, this will appear to be where? Let me take two light rays. Okay, is it going to be less than d1 or more than d1? Okay, so we can find out very easily. It's like this. Okay, so this light ray is going from denser to rarer medium. Denser to rarer, it is going to bend away from normal. It is going to bend like this. Okay. So this observer is receiving these two, okay, light rays. So for this observer, the object will appear to be here. This becomes the apparent position. This becomes I1. This is my object. The distance is going to decrease. Okay. This becomes d1 dash. d1 dash is going to be equal to d over mu. d1 over mu. Okay. So this d1 is mu times d1 dash. Okay, same thing will happen for someone who is looking from the other side. Okay, for this person also, the light rays are going to bend away from normal. Okay, the object will appear here. This is I2. So this becomes the apparent distance. This is also smaller than this. Do you see this? Okay, so here also d2 dash will be actual distance d2 over refractive index. Okay, so what is d2? It is mu times d2 dash. Okay, and both are given. Okay, so d is d1 plus d2. It is mu times d1 dash plus d2 dash. 1.5 times 4 plus 6. This will be 15 centimeter. This will be the depth of this slab. Okay, depth of this slab. Okay, do you see? Now the next one. Okay, this is 10 centimeter. So letters on page. If I have some letter here, this letter here, when I look it from outside here, all of the problems we are doing for near normal incidence. Okay, we are looking directly above this letter. When I am directly looking down on the letter. Okay, then it appears to be raised by 4 centimeter. Okay, the object appears here. Okay, it appears to be raised. This is 4 centimeter. Okay, I can directly use this relation. Either I can use this. Okay, d dash is going to be equal to d over mu. Okay, so what is d dash? This will become 6 centimeter. So 6 is equal to 10 over mu. Okay, what is mu? It is 10 over 6. So 5 over 3 becomes the refractive index of this glass here. Okay, I can also apply this relation. Delta is d 1 minus 1 over mu. Okay, this also I can do. So this is 4 is equal to 10, 1 minus 1 over mu. Okay, so 0.4 is equal to 1 minus 1 over mu. 1 over mu is 0.6. Okay, so 6 over 10. This gives me mu 10 over 6. Both forms are useful. Okay. Now this form is useful in several other cases also. Okay, let's look at them. What is apparent depth of liquids? Okay, first case. Okay, let's say that I have water. This is water. Water is filled in a container. Okay, let's say it is 30 centimeter. 30 centimeter. Someone is looking from outside. Okay, looking directly below on the bottom. It's a very common experience. The bottom appears to be raised. The apparent depth of liquid appears to be lower, smaller than the actual depth. Okay, what will be actual? What will be apparent depth? Actual depth is 30. Okay, and what if I have more than one liquid? What if I have two liquids? Let's say I have water here and I have oil. This is oil. Okay, this mu is, let's say, 1.5. Okay, and this is water here. Water mu is 4 over 3. Okay, now this is, let's say that this is 30 centimeter and this is let's say this is 15 centimeter. When I look from outside here normally down on the liquid, what will be apparent depth? Okay, can you find it? Try to do it. In the first case, we can directly utilize either the relation for apparent depth, or we can also do it for shift. Okay, in this case here, d dash, what is the meaning of apparent depth? Okay, if there is an object here, this whole bottom I can consider as an object. Okay, its actual position is here, 30 centimeter. Where it will be its apparent position? That is the apparent distance from this interface. It is going to be equal to d over mu. Okay, this is 30 over 4 over 3. So 90 over 4. This will be 22.5 centimeter. Okay, 22.5 centimeter. This will be the apparent depth. I can also find it using this formula for shift. 1 minus 1 over mu. This will be equal to 30. 1 minus 1 over mu becomes 3 over 4. Okay, this becomes 30 over 4. This is 7.5 centimeter. What is this? What is this? This is shift, apparent shift. That means this bottom will appear to be raised. This becomes delta. Okay, then what will be d dash? D dash. This is d dash. Okay, it will be equal to d minus delta. Okay, so 30 minus 7.5. This becomes 22.5 centimeter. Okay. Now in this case, this relation is very useful. Okay, I can write like this: delta is equal to delta 1 plus delta 2. Okay, try finding answer. Okay, so both will create some shift. Some shift will be created by water, and some shift will be created by this oil. What will be total shift? This is going to be equal to delta 1. Because of this, it is equal to 30, 1 minus 3 over 4, 1 over mu, plus, this is 15, 1 minus, this is 3 by 2, it becomes 2 by 3, 2 by 3. This thing will be same as here, it will be 7.5, plus, this is 3 minus 2, 1 plus 5. This is 12.5 centimeter. 12.5 centimeter. Okay. This is, what is this? This is a shift. You see, try to be careful here. This is not apparent distance. This is not actual distance. The actual distance is 15 plus 30. Okay. This is shift in the position of this bottom, this object which is kept here. Okay, it will appear to be raised. It will shift by this distance. Okay, so what will be apparent distance? Apparent depth. Okay, d dash is equal to d1 plus d2 minus delta. Okay, this becomes 15 plus 30 minus 12.5. Okay, so 32.5 centimeter. Let's look at one other method of solving the same problem. Okay, you see, if I have a single liquid, if I have this single liquid, this actual depth is d. Okay, in that case, d dash will be equal to d over mu directly. Now, if I have many liquids, for example, here, or here, let's say I have many liquids like this. Okay, this is mu1. Okay, and the distances are here like d1, d2, d3, mu2, mu3. Then I can, and if someone is looking from air, remember this. If someone is looking from air, if someone is looking from here, from this medium, then it becomes little different. It's different and little difficult. Okay, we are not doing those cases. Okay, we will do those cases in advanced course. Here we are just looking at the basic things. Anyway, this relation always holds. The relation that we discussed in the very beginning, u over mu1 is equal to v over mu2. This always holds. Okay, but then how to apply this relation in cases like this? So we will have to do it like little more carefully. Okay, so you should not be worried about that. Okay, that we will worry about in the advanced course. Okay, not here. Okay, in these cases, if I have many liquids filled up in this container and someone is looking from outside, okay, in that case, this d dash will be simply equal to summation of all this. Okay, that means d1 over mu1 plus d2 over mu2 plus all the liquids. Okay, we can apply this thing here also. Okay, let's apply that. Okay, so d dash is equal to d1. What is d1? This is 30. Okay, so this is 30 over 4 over 3 plus this is 15 over 3 over 2. Okay, this becomes 90 over 4 plus 30 over 3. This is 22.5 plus 10. This becomes 32.5 centimeter. You see the same answer we get. Okay, All right. Okay, let's look at one very interesting problem. Okay, one very interesting problem here. It's like this. Question. I'm going to just simply explain this problem and okay. Let's say that this is my water. Mu is 4/3. It is water. Okay, and there is a fish here. Okay, you see there is a fish inside. This fish is moving upward. Let's say it's moving like this. Okay, with some velocity. With some velocity, let's say how much? Let's say 2 meters per second. Okay, 2 meters per second. Okay, fish. This is fish. And here in the air, let's say that I have this bird. Okay, how do I draw the bird? Okay, it's a little. Okay, not little, but a lot. Okay, let's say that this is bird. Okay. Well, you imagine it. Imagine it to be a bird. Okay. Now this bird is coming down with some speed. What is speed? Let's say it is coming down with let's say how much? 3 meters per second. Okay. 3 meters per second. Okay. So this is water surface. Bird is above the water surface. Fish is below it. The fish is moving upward. The bird is moving downward. Okay. Now, question is what is velocity of first fish as seen by bird, and second velocity of bird as seen by fish? What do you think? What it is going to be? What it is going to be? Okay. Can you answer this? Answering it is not very difficult. It's like this. D dash is equal to d over mu or mu times d. Okay. When you simply differentiate with respect to time. This is the actual distance. When the bird looks on the fish or fish looking on to the bird, okay, both will see the apparent distance of each other. Okay, it is going to be either this or this. Okay. Now, when they move, when the fish, let's say that the bird is seeing the fish. Okay, the fish is moving up. So when the fish moves, its actual distance changes. When the actual distance changes, the apparent distance also changes. Now the rate at which they are changing is velocity. So when I simply differentiate it, then I get apparent velocity. It is going to be either v by mu or mu times v. Okay. So finding velocity also I can apply the same relation, exactly same relation. This is apparent velocity, actual velocity over mu or mu times actual velocity. You either divide by mu or multiply by mu. Same relation. If it is d by mu, it is v by mu here. If it is mu times d, it is mu times v. Exactly same velocity. Okay, so for bird is in air. Bird is in air. Okay. Now, assuming as seen by bird, okay, d dash is equal to d over mu. For fish, okay, assuming bird to be at rest. I am assuming that bird is at rest, only the fish is moving. What will be apparent velocity of fish? Apparent velocity of fish. Okay, v dash is going to be equal to v over mu. What is v? It is 2 over 4 over 3. It becomes 1.5 meter per second. Think about it. Is this right? That is when the bird does not move. Okay, if bird also starts to move, bird also moves, then relative velocity. Now both are moving in opposite direction. Opposite direction. What will be relative velocity? It is going to be added. Okay, it is going to be equal to 3 plus 1.5. This becomes 4.5 meter per second. Okay, so this is the velocity of fish as seen by bird. Okay, let's do it for the fish as seen by fish. Okay, as seen by fish. Assuming fish to be at rest, apparent velocity of bird is mu times v. Okay, it is mu. Okay, this is 4 over 3 times, this is 3. Okay, 3. This becomes 4 meter per second. Okay, now if fish also moves, then they are moving in opposite direction. The velocities are going to add. Okay, for the relative velocity. So if the fish also moves, it is going to be equal to 2 plus 4, it is 6 meter per second. Okay, mind it, they are not equal. They are not equal. Relative velocity of A with respect to B here is different from relative velocity of B with respect to A. They are not equal because the mediums are different. The mediums are different, that's why. In the same medium, they are going to be same. If both are in the same medium, in that case, it is going to be same. Okay. Now, one very special case, when let's say that I have a fish here. Okay. I have a fish. Okay. Now the fish is moving with some velocity which is parallel to the water surface. It is parallel, and I am looking at the fish from here. This is mu. What will be velocity of fish? Will it be velocity of fish? Will it be mu times v, or will it be v over mu, or it will be v? Which one is correct? What do you think? Think about it. I'm going to answer. it. It is not this. It is not this. It is this. Why? Because this fish is moving parallel to the water surface. Parallel to it. Okay. So its distance at every time it remains the same. It remains same. Okay. That's why the velocity is going to be same. The velocity changes only perpendicular to this water surface, not parallel. Okay, do you understand? Now, one other interesting problem. One other problem. Okay, it's like this. Let's say that I have this container and water is kept in this container. Let's say that this is water. Okay, got it. Now, let's say that I have one object here. Okay, this is my object. It is kept here. Okay. This distance, note down the problem. This distance is 15 centimeter. Okay. And this depth of this liquid water, this is also 15 centimeter. Also 15 centimeter. This is water. Mu is 4 by 3. It is water. Let's say. Okay. Let's say that it is water. Or let's say that it is something different. Let's say it is 60 centimeter. Not 15, but it is 60. 60 centimeter. This also is 60 centimeter. 60 centimeter. Okay. I have two observers. This is first observer, person 1. This is second observer, person 2. First and second. Okay. And then this bottom, on the bottom I have a plane mirror. A plane mirror. Okay. Locate images. Locate all the images as seen by both persons. Okay. Okay. Report distances from water surface. Let's say. Let's keep it common, water surface. Try answering this. What do you think? I have this container. In the container, okay, water is filled up to this height 60 centimeter. I have an object at a height of 60 centimeter from water surface. There are two observers, P1 and P2. The bottom of container is actually a plane mirror. How many images will be seen and where they will be seen? At what distances they will be seen? At what distances they will be seen? Okay, can you find it? Think about it. Okay, you should actually pause the video here. Right now you should pause it. You can resume it later. You can resume it tomorrow. That's not a problem. Okay. Try to answer this on your own. Try to answer this on your own. You will learn a lot of things when you answer it. I'm giving you a hint. Okay. Start by drawing the ray diagrams. Okay. You take two rays. Okay. You take one ray here, which falls normally. Okay. Now this ray will pass undeviated, and then it will start to retrace also. It will retrace. It will retrace. And then you take any other ray like this. Let me say that this is here. I will write 60 centimeter. Let's take any other ray like this. Okay. This ray is entering denser medium. It will deviate like this here. Okay. For the mirror and for this person, the person is inside water. Okay. The person is here. This person P2 is inside water. Okay. So I can take it to be anywhere. Okay. The person keeps on moving. Let's say this person will see that the image of this is somewhere here. The object appears to be here. This is the first image I1, which will be seen by this person. Now, what this mirror will think? What this mirror will think? This mirror will think that there is an object here, I1. This becomes an object for this mirror. So it will make an image at same distance. Okay, so this light will actually be reflected. The light will actually be reflected, okay, from here. So when this person extends these light rays, okay, there will be one image here. Now who will be able to see this? This light ray, and this light ray, these two light rays are reaching this person. So this person is able to see this image I1 here and I2 here, both. This person will see two images, one image here and one image here. This light ray has not yet reached person P1. This light ray will reach person P1 after refraction. After refraction, so this light ray is going to bend. It is going to bend. Okay, so this person is receiving this light which is reflected from the mirror. It goes all the way up. This light which goes up and this light. Okay, so when for this person, okay, one image will appear here. This is I3. So person P1 will see I1 and I2. Okay, and person P2, no, this is P1. P2, this is P2. P2 will see I1 and I2. And person P1, which is outside, this person will see only I3. We have to locate these images. That is, I have to find the distances from this water surface. Okay, and this can be solved very easily if you just keep in mind that apparent distance d dash is going to be either this or this. Either this or this. That's it. Can you find it? Okay. Let's try to see. Let's try to find out. I just have to draw the ray diagram. Just the ray diagram. And immediately I will start getting the answers. Immediately. I will start getting the answers. Okay. Let's draw the ray diagram. Okay, this is my water surface. Okay. Let's say that my object is here. I have my object here. Okay, this is my object. These two distances are same. This is 60 centimeter. This also is 60 centimeter. Okay, that's fine. Now this is my point. This is object O. This is point P. One light ray. It hits the interface normally, okay, does not deviate, plus it will retrace because this is a mirror here, a plane mirror, okay, a plane mirror, okay, alright. Now it will go on like this. This becomes my one refracted. Now, let's take one other. Why other? Because I need at least two light rays. I need at least two to make the image. This is the original direction. At this point, light ray enters the denser medium. It is going to bend towards the normal like this. That's how it is going to bend. Okay. And when I extend it behind, okay, this is where they are going to meet. This becomes my first image, I1. What will be this distance? This distance d dash is equal to mu times d. Apparent distance clearly is more than actual distance. It is going to be mu times d. Okay. What is mu? 4 over 3 into 60. Okay. This becomes 80 centimeter. This becomes 80 centimeters. Okay. From where? From the water surface. From the water surface. Now, this light ray hits the mirror and it gets reflected. It gets reflected. Now, for this mirror, this becomes an object. What is the object distance? Okay, for this mirror, this becomes object. I1 becomes object. What is object distance? It is equal to 80 plus 60, it becomes 140 centimeter. 140 centimeter. That means, what it means is actually, okay, what it actually means is, if I extend this here, okay, this distance is going to be 140 from here to here. This becomes my second image. This will become 140 centimeter. Object distance is equal to image distance from this plane mirror. Are you able to understand all of this? I hope you were able to see clearly. Okay, I guess so. Okay, makes sense. So this is the second image. This image will be seen by which person? P2. P2 is here. So this person is receiving these two light plus these two light. Okay, this person will see both images, I1 as well as I2. Okay, now this light ray, it cannot pass undeviated, it is going to deviate. Okay, it will deviate like this when it passes into the air. Now here I have another person. Okay, now for this surface, this becomes an object. This becomes an object. What is the object distance? What is this object distance? This is equal to 140 plus 60. This is 60. It becomes 200 centimeter. Okay. Now when I extend it backward, it is going to meet somewhere here. This is I3. So this person will be able to see this image. This image. This person is receiving this light plus this light. So for this person, the light rays seem to be coming from this point here. So this person will see an image here, I3. Now what will be this distance? Okay, this distance. Okay, this becomes d dash from water surface. Now this is going to be equal to d over mu. Okay, d over mu, because it is smaller than the actual distance. It is going to be equal to 200 over 4 over 3. This becomes 150 centimeter. Total 3 images. First image from water surface. First image 80 centimeter. Second image here from water surface 200 centimeter. And third image from water surface, it is 150 centimeter here. 150. Okay, 3 images. Okay, practice few problems. Next class we are going to continue with same discussion.